Okay, then how about magnetic force acting on electric charges? You know, the electric charges interact directly with the electric field, and as a result, the direction of the Coulomb force was parallel to the direction of the electric field, right? But in the case of magnetic field, they interact with electric charges only if these charges are moving, right? So therefore, this moving means that you have to think about its velocity vector. Okay. So take a look at the figure on the right side. It shows you an example of the results of a real experiment. A very interesting experiment in which the gamma ray splits into two charged particles, one electron and the other positron. Gamma ray is a very high energy light, and positron is just like electron, but it has a positive charge. Very strange, right? But they do exist, and if certain conditions are met, this gamma ray really can split into an electron and a positron. Okay, so in this figure, we have the magnetic field vector like this, which means that this magnetic field is going directly into the screen. Okay, and then this arrow on the top indicates the original direction of the gamma ray, and then looks like it's splitting into the electron and a positron at this location. Okay, and because of the conservation of momentum, this electron and also positron will still be moving along this direction. So this is their velocity vectors. Okay, and then these white curved lines indicate their motion. So electrons are shown on the left hand side and positron shown on the right side. So let's consider positron first. So it looks like it's almost doing a circular motion, right? So its velocity originally along this direction is changing. For example, over here is going like this, and here is going like that. These are the velocity vectors, and it's almost doing a circular motion. And in order to do the circular motion, you need some kind of force pushing it toward the center of rotation, right? We call this centripetal force. So here the magnetic field, magnetic force will work as a centripetal force, and then the direction will be like this. This is the direction of the magnetic force vector, depending on where it is and where the velocity vector is. Okay, so here what we find is that first the magnetic force is first perpendicular to the velocity vector, and at the same time it is also perpendicular to the magnetic field vector. Okay, so therefore we can now write that magnetic force vector is equal to the cross product between the velocity vector and the magnetic field vector, and velocity of what? Of course, it is the charge. So we also have to multiply by the charge. Okay. And how about electrons? Well, electron is just like having a negative charge here. So therefore, naturally, for the same velocity and same magnetic field, the direction of the Coulomb force, the direction of the magnetic force will be opposite. So therefore, originally for the positron, the magnetic force vector was along this direction, but now for electrons, the direction of the magnetic force will be like this. And so as a result, after a certain time, the velocity will be pointing this way, but then the magnetic force will be like this, and then for velocity going like this, magnetic force will be acting like this. Okay, so situation is the same between electron and positron, only the difference is their sign of the charges. As a result, the force will be opposite. And again, the same thing, but try to compare between the electric field and magnetic field. Originally, you get this from the force that you experimentally observe. You have to divide the force by the charges, but in the case of magnetic field, you need the velocity here too. Okay, And this is exactly why you had the unit for the magnetic field to be Newton divided by Coulomb meter per sec. Okay, right? And then what is Coulomb per sec? That was the current, right? So this is again equal to Newton per ampere meter. Okay. And again, we can also say that the magnetic field vector is along the direction where moving charges experience no force. What does it mean? You know, when this charge is moving along the direction of the magnetic fields, then these two vectors will be parallel to each other. And when you make a cross product between two parallel vectors, it will become zero, right? So which means that if the charge is moving parallel to the magnetic fields, there will be no force. So this is what it means, okay? And finally, we want to use a diagram to visualize the relationship between these three vectors, and it will be convenient to use the right-hand rule. Okay, what we mean by right-hand rule is that when you make a cross product of, for example, cross product between velocity and then the magnetic field, you have the magnetic, you have this velocity vector first, right? So imagine that you are using your fingers to encircle this and making a circle, right-hand circle, which goes counterclockwise when seen from the top. And then you will come across velocity vector first, and then come across the magnetic field vector. So that's what you are doing. You actually make a cross product between these two vectors. First, velocity vector and magnetic field vector. Then the direction of your thumb. Your thumb will be the direction of the force, right? So I will say that this is parallel to the direction of the magnetic force. Okay, this is how you remember it. And in fact, this was the case of positive charges. And if you have a negative charge, then again do the same thing, but remember you have to flip the direction of the force, because now you have the negative sign in front here, right? Okay. And let me ask you a question here. How the acceleration by a magnetic field change the kinetic energy of the charged particle, and how is it different from the acceleration by an electric field? You know, in the case of electric field, the force was directly along the direction of the electric field, so therefore there will be an increase in velocity, which means that there will be an increase in kinetic energy, or decrease depending on the direction. And then how is it? Is it also the case for the magnetic field? We will discuss this in the classroom lecture on Thursday, so please think about it by yourself, and we will study in the classroom lecture. Okay, and here we will study the circular motion of charged particles in a magnetic field to a better detail. Okay, so in the previous slide, the electrons and positrons did not really perform circular motion, and it was because of the friction due to the some kind of particles filling the space. But in here, in this figure, it looks like this particle is making a complete circle. So it suggests that this space is cleaner with less friction, okay? And here we have this magnetic field going again directly into this screen. And then the velocity vector is again perpendicular to the magnetic field. And then there is a centripetal force acting both perpendicular to the magnetic field and then the velocity vector. Okay, and where does this centripetal force come from? Of course, it is the magnetic force. Okay, and we learned that magnetic force is charge multiplied by the velocity and the magnetic field. So here, why we do not have the cross product? Because they are already perpendicular, right? So we do not need the vector. And what is this? So here, actually, it does not matter whether we have positive or negative particles. So therefore, we actually need only the positive value. So that's why we have this sign for the absolute value. And if you remember what you have learned about this circular motion from the spring semester, this is the centripetal force for the particle with the mass m, with the velocity v, and then this r is the radius of motion, okay? And then by rewriting it, you can figure out that this radius of the circular motion, for example here, okay, this much will be the radius of the circular motion. It is the mv divided by qb, okay? So what does it suggest? For the same particle moving at the same velocity, if you increase the size of this magnetic field, then radius will decrease, right? Okay, and then for the same magnetic field and same mass, if the initial velocity is larger, then radius will also become large. Okay, that's it. This is what you can figure out from this equation. And there are many other things we can learn. Okay, period for one, full revolution. Okay, this was a typo. The period of one full revolution is the time taken to make one complete circle. Okay, so we can calculate this value by dividing the length of the one full circumference by the velocity. Okay, so one full circumference is of course 2 pi r. So if you divide by v, and this is what you get. Okay, maybe I don't have to explain. You can just watch it or read it. Okay, and how about the frequency? Frequency is about how many times it repeats the same thing per unit period of time. Okay, so it will be very convenient to remember frequency. Frequency is simply an inverse of the period. Okay, so therefore we already calculated the period, so simply take an inverse. And how about angular frequency? Well, angular frequency is similar to the frequency, but if frequency is about how many times, angular frequency is about how much angle. So one repetition will be corresponding to 360 degrees or 2 pi. So therefore, simply multiply 2 pi to the frequency, then you will get angular frequency. Okay. And okay, so the above case here, here we assume that magnetic field was already perpendicular to the velocity. Okay, and then you will perform complete circular motion. But in general, the magnetic field may not be parallel to the velocity, right? Once you have some kind of magnetic field, this particle may be moving along any direction, right? So for example here, so here we have the magnetic field going like this, and then this velocity vector is pointing at an arbitrary direction, okay? But then how can we understand what is going to happen in this case? So, the velocity is a vector, so we can split this velocity vector into two components. One component parallel to the magnetic field, and the other component perpendicular to the magnetic field. And then think about them separately, and then combine later. Okay. So first, in the case of this velocity vector parallel to the magnetic field, we learned that by making a cross product, it becomes zero. So there will be no force acting on the velocity component parallel to the magnetic field, right? So there is nothing changing along this vector. So which means that this particle will perform continuously constant velocity motion. Okay. But in contrast, along the velocity vector perpendicular to it, there will be exactly the circular motion as we have studied here. So in this case, the radius of the circular motion is determined not by the size of the original velocity, but size of the velocity component perpendicular. Okay, and that is actually the size of the velocity, original velocity, multiplied by the sine phi. In this case, phi will be the angle here. Okay, so it will perform the circular motion due to the velocity component perpendicular to the magnetic field, and at the same time it will perform constant velocity motion due to the velocity component parallel to the magnetic field. As a result, it will undergo this so-called helical motion as shown here.